Hey physics kids, Mr. Johansson here. We're going to be talking about Ohm's law today. And Ohm's law, well, it looks at how much resistance any element in a circuit is causing for the electrons to try to go through. Everything resists electron flow, some not very much, some a great amount. The only thing that doesn't resist at all is called a superconductor, and that's a whole separate topic. If superconductors are ever made to be room temperature, that will change everything. Watch for it in your lifetime. You would be surprised at how many cool things will happen. But for everything else, there is resistance. It is not futile. So what is resistance? Well, resistance measured in something we call ohms. The amount of resistance is equal. It's a ratio of how much voltage in volts you have to push electrons through to achieve a certain current. All right? And the current is in amps. So the variables would be V and I. Got that? V and I. So you could say R equals V over I. And that is Ohm's law. Now, technically, this is not really a law, and I'll explain that in a minute. However, its relationship is so profound that we use it all the time as we're talking about electricity. So, 1 ohm of resistance is the amount of resistance where 1 volt will push along 1 amp. Okay, so how hard would I have to push to get 2 amps to cross? Well, 1 ohm would be the same. If I had 2 volts, that would make me able to push 2 amps, like that. So the amount of resistance is going to be very important and also fairly easily measured in a current. All right, wires have very low resistances. But there are some devices that are made to have very specific resistances. They're called resistors. And in every circuit, you have almost always a variety of different resistors. A light bulb itself is a resistor, although I will show you a light bulb doesn't necessarily follow Ohm's law. So let's just try a problem, shall we, using that Ohm's law? Be aware then that the units of resistance are going to be volts per amps. And we don't need to go lower than that in terms of the units we're using. Units are still, of course, important, but this is how we'll work the units here. So what's the current through a 50 ohm resistor with a potential difference of 200 volts? Let's look at that. So the givens, voltage is 200 volts. And it says the resistance is 50 ohms. To make the ohms sign, the variable is actually this Greek letter omega. Ohms, omega, kind of makes sense. All right, so, and we want to know what kind of current that would have. So the formula is R equals V over I. We need to solve for I, so if we multiply both sides by I, they cancel here, so V equals resistance times current. To substitute and solve, voltage equals, I'm sorry there, R equals V over I. I'm looking to solve that. Multiply both sides by I. I don't know where I was going on that, but IR equals V. And now if we get rid of the R, okay, so I equals V over R. Let's be more careful as we do that, shall we? Thank you. So we have current equals volts divided by resistance. Let's see how that works out. Volts are just in volts. Resistance has the units of volt per amp. Invert and multiply, or rather just multiply both sides by reciprocals to cancel everything, but then you have to do the top. Amp over volt, the volts cancel, so I will be left with amps. So this is looking good. You following along carefully? I hope so. All right. So I equals V over R equals 200 volts divided by 50 ohms, and we already got the units to work. Well, that's going to equal 4 amps. Simple as that. Okay? So just basic Ohm's law is always relating voltage, current, and resistance. Now, let's do an electric circuit, all right? For that, we're going to need to identify what some of these schematic symbols would mean, so you'll understand the shorthand that we use when we're diagramming electricity. Okay, so let's take a look at all that. I'm just going to give you a short list of some of the electrical symbols. This is certainly not an inclusive list, but a resistor is going to look like that. And in many problems, you will see me write 3 lines under it. What do you suppose those 3 lines are? They're the 3 variables for Ohm's law. So this might be a 50 ohm resistor, and then I would want to know, well, if I gave you the current or the voltage, you could calculate the other one. So anytime you have a resistance in a circuit we're solving, generally you're going to have to put down the 3 variables in Ohm's law. The resistance is usually given. We can also have a resistor that looks like this, and that's a variable resistor. When you tune a volume knob or turn a volume knob, you're changing the resistance. That's why the speakers sound louder or softer. A battery looks like that. These are the individual cells in a battery. A switch in a circuit would look like that, right? You just press it down and the switch is activated. A very important understanding we're going to have here is that's a voltmeter. It measures voltage. This is an ammeter, and it measures current. Now, hooking a voltmeter up and an ammeter up turns out to be a very important thing to understand how to do it correctly. The reason, in electrical terms, we say if you do not connect them right, you make smoke. In other words, you start burning stuff up. One of them will simply turn a circuit off, for the most part. The other will do that make smoke thing, and trust me, you don't want to do that. So, when we want to talk about circuits, we're just going to be using these things. And I'll show you how a voltmeter and an ammeter would get hooked up a little bit later on. Right now I'll just put them into the circuit. But as we discuss series and parallel circuits and the ideas behind it, we'll talk then why voltmeters get put in parallel to a resistor, and why ammeters have to get put in line to a resistor. And that also gives us an idea of what the internal resistance of both a voltmeter and an ammeter would have. And it also gives you the reason why, if you get it wrong, you're going to make smoke, why this would be a bad thing. So, how do we control current in an electric circuit? Let's just draw a quick electric circuit. There's a battery, there's a resistance. So the battery increases the potential difference amongst the electrons, gives them some electrical pressure, and the resistance decreases the electrical pressure. Okay? So, well, if I put some numbers in here, how about if I say this is a 60 volt battery, and we have a 30 ohm resistor here. Now, using Ohm's law, what are we going to have? All right? Well, Ohm's law solved for current is I equals V over R. So we'll just put the things in here. So 60 volts over 30 ohms gives us 2 amps. So everywhere in the circuit, now realize this, everywhere in the circuit we have 2 amps flowing. So if I were to put an amp meter here, and that would go directly in the circuit, all the current has to pass through it because it's trying to read all the current. So if I put an amp meter in here, it would read 2 amps. So the question would then be, what if I wanted there to only be 1 amp of current flowing in this? How do I do that? Well, there's 2 ways to do that. If I put, say, a 30-volt battery here with a 30 ohm resistor, well, 30 volts over 30 ohms would give us 1 amp. And that would reduce that to 1 amp. What if I was not able to control that voltage or wanted to do it a different way, so I left it at 60 volts? Oh, I'm back up to 2 amps then. How can I change that? What about the resistance? What if I was to change this to a 60 ohm resistor, right? Then I have 60 volts over 60 ohms, and that will again give me 1 amp. So those would be the ways I could control the circuit, control the current in a circuit. We use that all the time. One situation where Ohm's law is not a law, it breaks down. Well, the amount of resistance in a substance has to do with its temperature. The higher the temperature, the electrons in it are vibrating and messing about so much that they impede or get in the way of the easy flow of electrons through it. So when you make a resistor higher temperature, it becomes more resistive. If you make it much higher, it becomes much more resistive. When I turn on an electric light, if I turn on an old-fashioned incandescent bulb, what happens to that? Well, immediately, bang, it's on. How's that possible? It needs to be well over 1,000 degrees Celsius in order to be bright and on. How does it go from almost 0 degrees Celsius to full 1,000+ degrees Celsius in an instant? I'll tell you why. That conductor is meant for very, very high temperatures, which means at very low temperatures, it doesn't resist much at all. So when you turn that on at that very low temperature, current dumps across it enormously. There's a huge amount of current that goes through and heats it up in an instant. You don't even tell. You can't even tell that it's going red, orange, yellow, brighter, brighter, bright. No, no, no. It's on. All of that current goes through and makes it incredibly hot really fast, because it's letting a vast amount of current through for what it will normally do. Once it's up to operating temperature, which took a tiny fraction of a second, once it's at operating temperature though, now its resistance is what its resistance is meant to be. It becomes much more resistive and does not allow electrons through easily at all. If it cools down, it'll allow more to go through. So it comes up to a temperature and stays at that temperature because it will make it more resistive for electrons to try to pass. So a simple light bulb shows you how Ohm's law is really not a law, but we still use it all the time. Also consider, at least with those old incandescent, the bulbs with the filaments in them, when do those bulbs blow out? Do they blow out when they're on? They're just on and suddenly they blow out? That does happen, but it's rare. Most of the time when they blow out, it's when you first turn them on. Because all at once, they go from 0 to well over 1,000 degrees in an instant. And that means they also heat up tremendously and expand tremendously. And if they've been expanding and contracting for so long, they get a weak spot in them and they expand and they break all at once. So when you turn them on, that's when they go out. When you turn them off, not so much, because they cool off more slowly. But when they heat up, that all takes place so fast. So gives you an idea of Ohm's law not exactly being a law, but we're going to use it all the time, and it works pretty much all the time. Hey, thanks for watching. Happy physicsing.